Today we're starting a new portion of the class. We're going to start learning about our first non-linear circuit component, and I'll explain what I mean by that in a little bit, and that is the diode. So the term diode actually comes from the days of vacuum tubes. Diode meant that there were two metal electrodes inside this vacuum tube. I can talk more about that if people want to know, but vacuum tubes are not terribly important for the course. So the term stuck today. Maybe I'll explain the connection between the two later. But when we say diode, we really mean solid state diode. So this is not important for you guys to know, but the inside of a diode is silicon, and there are two different regions of this piece of silicon. There's one that is p-doped and one that is n-doped, and we don't have to worry about any of this. This is just kind of for fun. So the idea is these parts of the silicon are made chemically different by adding boron or arsenic or other what they call dopants, other atoms. And the fact that these two regions are chemically different means that conduction of electricity between them is asymmetric, and that's what we haven't seen before, right? We haven't seen a component where the current flow in one direction is like mathematically different than the current flow in the other direction, and that's what we have with diodes. Okay, that's all the more we'll have to talk about the inside of diodes. So our ideal diode looks something like this. So if we draw a graph of current versus voltage, our ideal diode admits no current through for voltages in a certain direction. So this is zero everywhere, zero current. And then for a positive voltage, as soon as our voltage goes from being negative to positive, this goes perfectly vertically, where V equals 0 and I can be whatever it has to be. So these regions are, so the two possible situations are on the left here. This is the reverse or reverse bias region where there's no current flowing, and here where we have current flowing, this is the forward bias, but we have no voltage difference across our diode. So over here, our diode is acting like an open circuit. It's acting like two disconnected wires. Here, our diode is working like a perfectly connected circuit. It's looking like a ideal wire. So like for this part, and you can kind of see this from the slope on our IV graph, this part is like the resistance is really, really high. And here, it's like the resistance is 0. Okay, so this is the ideal case. Of course, we don't have ideal diodes. We have actual diodes made of silicon, and their curve looks a little different. We'll draw one version of the graph, and then we'll kind of zoom in on some parts of it. So the actual diode graph looks kind of like this. It is actually an exponential that is just slightly shifted. So this is still our current. This is still our voltage. And this is a total cartoon, so let's look at some more detailed spots. Excuse me. So in this forward direction, what we call the forward biased region, this is just in the upper right quadrant. We pass through the origin, and our graph of current versus voltage is actually an exponential. So this exponential is I equals I naught times E to the V over NVT minus 1. So really the only thing we have to worry about here is I naught is some constant, like for a particular diode. I guess it kind of tells you how, like the size of the diode, like the physical size of the diode. V here is the voltage. Vt is a thermal voltage that only depends on temperature. So for different temperatures, you get different values of this denominator. And N here is some little correcting factor that we don't need to worry about. We're not going to use this equation. I just wanted to show you that this is that this graph does have the form of an exponential. Okay, so at 2 different points on this graph, let's just look at a point down here. So down here, we have some small voltage and very little current flowing, right? If we increase our voltage to, say, here, we definitely have an increase in voltage, but we have a much larger, proportionally a much larger increase in current. And that is what we mean when we say this is nonlinear. Doubling the voltage does not double the current the way it does for resistors and capacitors and inductors, for DC and AC circuits. All right, so so to make this picture kind of simpler, well, let me say this. We're not going to use this exponential equation. We're going to approximate this diode behavior, and we'll get to a more specific model for this approximation in just a second. But somewhere in between these 2 points, we can kind of break this diode behavior into 2 pieces. So like over here, it's not conducting very much current. Over here, it is conducting current. And the transition between these, we need to give a voltage to. So so this voltage is called the turn-on voltage, or the forward bias voltage. And so this is where the diode starts to conduct a significant amount of current. So this value depends on what the diode is made of. So silicon is not the only semiconductor. Silicon diodes have this turn on happen at about 0.7 volts. And germanium diodes, germanium is another semiconductor that is just under silicon on the periodic table, so chemically very similar. It turns on at 0.3 volts for GE germanium. Most of the diodes we will use in problems, and all of the diodes we will use in lab are silicon diodes. You certainly can buy germanium diodes, and they show up lots of places in real circuits. They're just less common. Okay, so this is what the forward bias region looks like in real life. Now let's look at this reverse bias region over there. I'm going to keep this graph up. So the reverse bias region looks like this. So we're drawing the lower left quadrant now. So here, our current is not quite 0. It's really close to 0, but it's really small. Typical values for this might be like 1/10 of a microamp, so 100 nanoamps, and you can certainly buy diodes with that have different values of leakage current, but maybe we'll say this is approximately minus 0.1 microamps. And I guess I didn't draw currents on here. I should. So maybe up at this point, this is like 20 milliamps. So this is like 10 milliamps. So we're talking about several orders of magnitude more current in the forward direction here than in the reverse direction. So this is a very small amount of current. This is very flat. And it continues flat until you reach a particular voltage called the reverse breakdown voltage. Sometimes it's just called the breakdown voltage. And at the reverse breakdown voltage, then your diode actually does start to conduct in the negative direction, and it does so very sharply. So this is basically, you are you are breaking the inside of the diode, forcing it to conduct electricity in the opposite direction. This is often bad for diodes. They are not designed to work in this region. Some diodes are designed to work in this region, and more on that later. But in general, the reverse breakdown is something to avoid. So this voltage might be minus 40 to minus 100 volts as kind of typical values. You can find diodes with reverse breakdowns definitely in the couple 100-volt region, I know, and probably higher if you're looking for special high voltage diodes. All right, so this gives us some sense of this behavior. So this graph, we might modify so this goes down like that. All right, great. So when we're looking at different points on this graph, let's look at this forward bias graph for just a little bit more. If our diode is under some conditions of voltage and current in the circuit, it is experiencing some point along this graph, right? So there's some relationship between the voltage and the current, and that is going to give us, a particular voltage is going to give us a particular point on this graph. So let's say we have a point like here, that this is a point like there. So let's say this point is 0.6 volts and 2 milliamps. So these are like, we could think of these as the coordinates of this point. So our diode, when it is at this point, is doing the same thing in our circuit that a resistor would be doing if it had a particular value of the resistance. Now that changes as soon as something changes in the circuit, right? Whatever resistor effect we have here is different than whatever resistor effect we have here, which is different than whatever resistor effect we have here. So, so the point being, we can talk about what's called the static resistance of a diode. And that is at a particular point, a particular combination of current and voltage, we can say, okay, under these exact conditions, our diode is doing the same thing as a resistor with what value? Well, R equals V over I. So 0.6 volts over 2 milliamps is equal to 300 ohms. So right here, our diode is doing the same thing that a 300 ohm resistor would be doing. We could look at a different point. So let's say we're looking at a point up here where we have a 20 milliamps and maybe 0.8 volts. So here, so 300 ohms was like this point. What did I say? 0.8 volts and 20 milliamps is going to give us a resistance of 40 ohms. So that is like what's going on here. So here it's like our diode has a lower resistance because for a small increase in the voltage, we have had a much bigger increase in the current. So the resistances of these lines are related to the slope of the lines that go through these points. So the slope of the line that goes through this point is the same as the slope, the I versus V slope of a 40 ohm resistor. It's just that this is the only point where that 40 ohms is true. This point, the slope of the line going through this point is the same as a 300 ohm resistor. And if we look at some point way out here where we have, let's say minus 20 volts and minus 1 microamp or something like that, here we have 20 mega ohms. So it's like our diodes have a really big resistance when we have them in this reverse biased region. Okay, so this is called the static resistance. We don't We probably won't need to use this to solve problems. This is just something to think about. Under these particular conditions, this diode is doing the same job as a resistor. Okay. Lastly, we can also talk about resistance in a different way, and that is the dynamic resistance. We also won't need to be using this, but it's also a useful thing to be able to think about. And the dynamic resistance is related not to the slope of the line that goes through one of these points, but instead related to the slope of the actual function. So the dynamic resistance here is related to the slope of this line that's tangent to that point. Or in other words, the dynamic resistance, sometimes a lowercase r is used for this, but we won't need a variable. It's equal to delta V over delta I. So that's the slope of the I versus V curve. So somewhere like here, where we have a very steep line, we have a very, very low dynamic resistance. A small change in the voltage can cause a really big change in the current. For a resistor, the static and dynamic resistance are the same thing, so that's why we've never had to worry about this before. Anyway, some people find this useful to think about, but we won't need to use the dynamic resistance for homework problems. I might talk about it later, later in other lectures. All right, so this is our introduction to diodes. We are going to, so the next video is going to be about a practical model for diodes and how to use that in solving diode circuits.